In this video, we're going to take a look at the Introduction to the Solutions unit for Grade 11 Advanced Chemistry. We're going to look at some introductory definitions and concepts, and then look at problem solving with concentrations in this video. Solutions we first looked at in our Grade 9 Advanced Science class last year, so some of these definitions are going to look familiar to you, but be sure you've got them in your notes. A solution is a type of mixture. So a mixture has more than one substance in it. To be a solution, though, the mixture has to be homogeneous. A homogeneous or homogeneous mixture is one where the composition of the mixture is the same everywhere. If you take some orange juice and some concentrate frozen orange juice and you put it in a pitcher and you add in 3 containers of water, at that point you have a mixture because you've mixed the concentrate with your water. But because you haven't stirred it, its composition is not the same everywhere. It's more concentrated at the bottom, it's less concentrated at the top. So that mixture would be heterogeneous. It would not constitute a solution. If you reached in and stirred it all up or shook it all up so that it was the same concentration everywhere, the same composition, at that point it would be homogeneous, and then you would say you have a solution. In the solution, the solute is the substance that is being dissolved. We're going to talk here about primarily solutions made by taking a solid substance and dissolving it in a liquid. So for us, the solute will be the substance being dissolved. That will almost always be the solid substance. Having said that, we will do some solutions made by mixing 2 liquids. For example, if you mix some methanol, a small amount of methanol, and a larger volume of water, you'd usually say that the smaller volume is the one that's your solute and the larger volume is your solvent. But keep in mind that solutions can also be other mixtures. The atmosphere, for example, is an example of a solution. If it's in say, the atmosphere within your classroom, in that set situation, the classroom atmosphere probably has the same composition everywhere in the room, so it would represent a solution. If you looked at the atmosphere in the wider context of the Earth, then it would not represent a solution because the atmosphere at the Earth's surface is a different composition than it is way up high on the edge of the outermost parts of the atmosphere. The solvent is the liquid in which you're dissolving your solute. So for us, the most common solvent will be water. We're almost always going to be dissolving our solutes in water. And when you're using water as your solvent, you can say that your solution is aqueous. Aqua means water, so an aqueous solution is one where water was the solvent. Having said that, we may also use alcohol or acetone. There are other solvents that are also commonly used depending on the type of solute that you're dissolving. Once you've dissolved your solute, you've made your solution, you may want to talk about the concentration of the solution. Your concentration is a measurement somehow of how much solute there is in a given volume of either the solvent or of the solution. In our Grade 9 class last year, we kept referring to concentrations in terms of grams of solute per 100 milliliters of solvent. So we would say there's 25 grams of sodium chloride per 100 mils of water. And we even had a little formula. Concentration was mass of solute over volume of water times 100. That was just one type of concentration unit. We're going to look in a moment at several other much more common examples of concentration in chemistry. A saturated solution is a very important term. A saturated solution is one where your concentration has reached its maximum possible value at a given temperature. We know that solubility of salts, again from our Grade 9 course, do depend on the temperature. Most salts, most solid solutes, increase in solubility when you raise the temperature. So we had graphs that looked like this. I can just move this over for a moment. We had graphs that had temperature on the x-axis and solubility on the y-axis, and for most of those graphs, solubilities of different salts increased like that. However, if you were looking at the solubility of gases with temperature, gas solubilities, first of all, are usually much lower than the salts, but they will always decrease with temperature. So where most salts increase in solubility with temperature, gases will decrease in solubility with temperature. Solubility is just another way to talk about the maximum concentration of a solution. So solubility is the concentration of a saturated solution. When we have a saturated solution in the lab, you might say that the salt has stopped dissolving. In fact, when we looked at this last year, we made saturated solutions by putting enough salt in the water. We did it pinch by pinch until the pinches of salt stopped dissolving. And so that in the end, after shaking and shaking and shaking, there was still a little bit of undissolved salt at the bottom of the test tube in the water. And at that point, you would have said that the solution you've made was saturated. But keep in mind that although you might say colloquially that the salt has stopped dissolving, or that no more salt is dissolving, in a saturated solution, salt is always dissolving, because a saturated solution is an equilibrium system. The salt looks like it's not dissolving because every time a solute particle dissolves, somewhere else in your solution, a solute particle that had dissolved recrystallizes, precipitates again. So the solute, if you consider a test tube, perhaps here's a test tube with a bit of solute in it, here's your solvent. Every time a solute particle escapes and dissolves, somewhere else a solute particle returns to the crystal, and so the mass of crystal to the naked eye stops changing. So we would say it looks like the solute has stopped dissolving, and so we are confident at that point that we have a saturated solution. Alright, when you're dissolving a solute in water, keep in mind from the perspective of particulate level that the solute particles themselves are attracted to each other. We remember from our unit on liquids and solids, very, very important idea of intermolecular forces, IMFs. The solute particles are attracted to each other. If you're talking about dissolving an ionic compound, a salt, the particles are ions, cations and anions in some kind of crystal lattice structure, and they're attracted to each other by pretty strong ion-ion forces. If you're talking about a molecular solute, a covalent solute, they're held together by London dispersion forces at the bare minimum, and then they may also have dipole-dipole forces if the compound is polar, or even hydrogen bonding in some cases. So why would a salt dissolve? Why would a molecular compound dissolve if its particles are held together strongly with IMFs? The answer is that the solute particles are also attracted, if they're going to dissolve, to the solvent particles. So the solvent particles experience IMFs between themselves, but when you put a solute into the solvent, there are now possibilities of forming new intermolecular forces between solute particles and solvent particles. If those new intermolecular forces are stronger than the original ones, then the substance, the solute, will dissolve. So we have a picture here of an ionic crystal with cations and anions. Can you pause the video here and just convince yourself which of the particles in the crystal lattice, the larger spheres or the smaller ones, which ones are the cations, which ones are the anions? If you looked over on the right here, or looked at how these water molecules are interacting with the atoms in the crystal lattice, you could actually have deduced it. The water molecules which are attacking these particles have negatively charged oxygen atoms and positively charged hydrogen atoms. So here's a hydrogen positive, and the oxygen is negative there. And here's another water molecule with a negative oxygen, positive hydrogens. And so in this particular case, one of the small atoms from the crystal lattice structure is being attacked by the negatively charged oxygen atoms. That means this little guy here in the middle must have been positive. So in the crystal lattice, these guys are positive and the larger ones are negative. So they were attracted to each other by ion-ion forces, but now the water particles are also attracted because water is polar, so the negative parts of water are attracted to the positive ions, and the positive parts of water are attracted to the negative ions in that crystal. When the salt dissolves, when an ionic compound dissolves, it doesn't simply enter the water as formula units. For example, when you dissolve sodium chloride, NaCl, you don't get NaCl particles generally floating around in the water afterwards. NaCl is made up of sodium ions and chloride ions. And when they dissolve, they actually dissociate. There's a very important word. They dissociate, so they break apart from each other. So where they used to be held together by strong ion-ion forces, those forces are overcome by the attractive forces of water molecules as well. So now the ions get pulled apart from each other. We say they dissociate. You could write a little balanced equation for that. You could say NaCl solid is dissociating into Na positive aqueous and Cl minus aqueous. So we take the solid substance and break it apart into its ions. That's called dissociation, or sometimes more generally ionization. In this situation, notice again that the water molecules are surrounding the ions, and they're surrounding them in a very particular way. It's very important you understand that. You might be asked to draw that on a test or exam. The cations are surrounded by water molecules whose oxygens are oriented towards them, and the negative ions, the anions from the salt, are surrounded by water molecules whose positive hydrogen atoms are oriented towards them. We say that those ions, after they've been pulled apart and surrounded by water molecules, they are then said to be hydrated. So the hydration is the surrounding of ions in solution by the water molecules in that way. Now we usually assume that dissociation is 100%. We usually assume that when a salt dissolves, all of its ions dissociate and get pulled apart completely from each other and hydrated. However, if you can imagine particles floating around after they've dissociated, every once in a while, a positive and a negative ion may actually come close together and collide, and they may form what's called an ion pair. So you may actually get less than 100% dissociation because of the formation of these ion pairs. Notice that the water molecules are still hydrating those ions, but because they came close together, they formed a pair. That pair may just be temporary. They may get pulled apart again as they get jostled by water molecules. But keep in mind that dissociation isn't always 100%. All right. Let's turn our attention to units of concentration. In chemistry, there are several units that you need to be familiar with. By far, the most important unit of concentration in chemistry is molarity. Molarity is defined as the number of moles of solute per liter of solution. Now that's very important. You notice that it's focusing here on the volume of the solution measured in liters, not the volume of the solvent, but of the solution. So a formula that's useful for this, I don't use formulas a lot, but this particular formula is really important. We say C is equal to moles of solute divided by volume of solution. Now the C here is used to represent molarity. It stands for concentration, where we almost always mean molarity when we simply say concentration. We don't use a capital M for its symbol just because we've already decided that capital M will stand for molar mass in a formula. Now the volume of the solution here has to be in liters. If you were to express a concentration in molarity, you might say that a sodium chloride solution has 0.20 moles dissolved per liter of solution. So there you've described the molarity, 0.2 moles of sodium chloride per liter of solution, but you might say that a little more succinctly as 0.20-M, capital M. Notice that this capital M is now a unit. It's not a symbol in a formula, but rather it's a unit. In the same way that in a formula you'd use a little m to represent mass, but then you might use the letter G to represent grams, which are a unit of mass. So here, the capital M following a number like this is a unit, and when it's used as a unit, it does not mean molar mass, it means molarity. However, you can also remind yourself of the definition of molarity by writing out simply 0.20 moles per liter, or what I'll usually write, moles per liter, like that. Okay? In algebra class, you know that 1 over x is the same thing as x to the minus 1. Therefore, moles over liters is the same as moles liters to the minus 1. Another unit of concentration, a little bit, this one's actually not as common, and for advanced placement chemistry, it's actually no longer going to be on the AP exam as of May of 2014. The molality is what it's called. The symbol or the symbol for its units are little m, and it's a scripted m with 3 little bumps like that, so I can distinguish it from a printed m with 2 little bumps. It is the moles of solute per kilogram of solvent. So if you want to write a little formula for yourself, molality is the moles of the solute divided by, now I could just say mass here, a little m for mass of solvent, but instead I'm going to actually write kg of solvent, just to remind myself that it's kilograms. Alright, and another unit of concentration, very familiar. We've used this one in our gases unit before. Mole fraction can refer to either the solute or the solvent. Here I'm describing the mole fraction of the solute. It's the moles of solute divided by the total moles in solution. For example, more clearly in a formula, the mole fraction of the solute would be the moles of the solute divided by the total moles in solution. If we assume there's only one solute and one solvent, then moles of solute plus moles of solvent. Now you could calculate the mole fraction of solvent in exactly the same way. Just replace the numerator with moles of solvent. However, if you have already calculated the mole fraction of your solute, you could say that the mole fraction of the solvent, since there's only 2 components in this solution that we're talking about, is 1 minus the mole fraction of the solute. Now that again assumes that there's only one solute in this solution. A fourth unit of concentration that you will see is called percent concentration, and it's complicated by the fact that it's calculated in at least 3 different ways. So percent concentration, you'll sometimes see percent concentration referred to as a mass percent. If it's a mass percent, it might also be called percent W by W. Those W's actually stand for weight. It's a commonly used symbol in American textbooks, but keep in mind that weight and mass are not actually the same things, but we'll treat them here as though they're the same. So the mass percentage would be the mass of your solute divided by the mass of the solution times 100. Now, by the law of conservation of mass, keep in mind that the mass of solution would be the mass of the solute plus the mass of the solvent. That's true because of the law of conservation of mass. Sometimes another common way to express percent concentration is to express it as a percent mass by volume or weight by volume. This time your denominator changes from the mass of solution to the volume of solution instead. And again, keep in mind that that's the solution's volume, not the solvent's volume. If you take 100 mils of water, there's 100 mils of solvent, and you drop in some solute, then the volume of the solution is likely going to be larger than 100 milliliters. So your volume of solution is usually going to be larger than the volume of the solvent that you use to make it. So don't confuse those two things. They're not equivalent. The third way to calculate percent concentration is used when there's a liquid as your solute and another liquid as your solvent. So for example, if you were dissolving alcohol in water, it might be more convenient to measure the volume of the solute because it's a liquid as opposed to its mass, although you certainly could measure the mass if you were careful on a balance, but you might prefer to express percent as the percent volume by volume. And now it's the volume of the solute, which is at this point a liquid, divided by the total volume of solution. Now, there is no law of conservation of volumes, so don't always assume that the volume of the solution is just the sum of the volumes of the solvent and solute. If they are meant to be, if you are meant to assume that, you'll be told in a question that the volumes are additive. When a question says that volumes are additive, it's telling you that you're allowed to assume that if you take 50 mils of solvent and add it to 50 mils of solute, you'll get 100 mils of solution. That's not always true, though, in the real world. If you take 50 mils of methanol and mix it with 50 mils of water, you'll get less than 100 mils of solution in the real world because those particles, when they mix, actually fit in between each other to a small degree. So volumes are not, in the real world, always additive, but in most problems you'll be told to assume that. One other note here before we leave and go and do some actual problem solving. You'll sometimes run across the unit of concentration, ppm, which stands for parts per million. Parts per million. There's another one related to it, parts per billion, which you'll see as well, perhaps in an environmental science class or in a biology class. Parts per million can be interpreted in two ways. It can be interpreted based on mass percents or based on weight by volume percent. If you're talking about a mass percent, then a parts per million is the number of milligrams of solute per kilogram of solution. So if you think of a kilogram is 1,000 times bigger than a gram, a milligram is 1,000 times smaller than a gram, so a milligram is 1,000,000 times smaller than a kilogram. That's why it's called parts per million. In a similar way, if you were doing a percent mass by volume, then parts per million now would be the milligrams of solute per liter of solution. All right, so keep that in mind. You may come across those in a couple of situations later. So there's just an introduction to the solutions unit. We're going to take a look at some solution calculation problems involving concentrations in a separate video.